Hi everyone, I'm DeliangWang. I'm from Machine Learning University. I'm going to present the paper A Generic Interpreting Method for Knowledge Training Models. As we know, KT is a machine learning technique that attempts to model learners' dynamic knowledge states on the scale level and predict their future performance. The process can be illustrated by the figure. And recently, deep learning techniques have been introduced to the training domains such as RNN and MANN. So deep learning knowledge training models have outstanding performance, but in the meanwhile, they often have complicated structures. They operate like black box. The decision process is untransparent, so we need to explain them. Actually, we have already explored interpreting them with the methods in explainable artificial intelligence, but the adapted XAI method called LRP is more specific, which means it can only be applied to models with certain structures. But as we know, normal models normally have various inner structures. Thus, it is a lack of the interpreting method that can be applied to different DLKT models. So to select a generic interpreting method, we look up the methods in the AI domain, and post-hoc interpreting methods are designed to explain deep learning models. They can be classified as generic and non-generic techniques. Among the generic techniques, we select deep sharp. Its main idea is to decompose the prediction of a sample to the sum of feature contributions through backpropagation. It has an assumption. It compares the interpreting sample with the reference sample and assumes their output difference is caused by their difference in the input features. For example, there is a learning model F, a sample X to be interpreted, and reference sample R to be compared. And their predictions are fx and fr. Deep sharp attributes their output difference in y to their feature contributions, as the equation shows, where c delta xi delta y represents the amount in the prediction difference delta y caused by the feature difference delta xi. To compute the c delta xi delta y, the process can be regarded as backpropagating the prediction difference in the y from the output layer to the input layer. Actually, the delta xi delta y between the interpreted sample and the reference sample is called reference-specific feature contributions, because if we know if we select different reference samples, we can get different reference-specific feature contributions. So to obtain reasonable feature contributions, it should select multiple reference samples, and the main of multiple reference samples. The main of multiple reference-specific feature contributions is regarded as the final feature contribution, and we apply it on DLKT models. Here is the point case. For example, if a learner has already answered the full question, learning DLKT model predicts that he has 0.5 probability to correct answer the next question on Q5, right? In order to interpret this prediction, Deep Sharp selects a lot of reference samples and make prediction, and then we compute the output differences between the sample X. The prediction of sample X and each reference sample. For example, the output difference between the prediction of sample X and the prediction of first reference sample is 0.75 minus 0.63. It equals 0.12, right? After obtaining the output differences, we backpropagate them from the output layer to the input layer, so we can get the reference-specific contributions of each question answer pairs. And then we come to the final stage. We perform an average operation on the reference-specific contribution of each question answer pairs. So here we got their final contributions. We call them question answer relevance. QA relevance is the KT task. And then we just design our experiment. Yeah, first we build DLKT models, then we interpret them, then we explore their hidden information. First, we select RNN-based EKT, MAN-based EKVMN, and attention-based SNKT, we pre-process the dataset participants 2009 and build them, train them. Here is the result, the performance of these models. And then we split the test data into sequences with a length of 15 for the interpreting purpose. The first 14 question answer pairs serves the input to predict the model's performance on the 15 questions. We applied it chart to these sequences and obtain the QA relevance for the first 14 pairs. But we have no idea whether the QA relevance is correct or not. So an illusion experiment is conducted. For positive predictions, we elect question answer pairs in the increasing order of QA relevance. For negative, we elect them in the increasing order of QA relevance. Then we observe the accuracy changes among the correctly and falsely predicted sequences. Here is the result. R represents random illusions. We can see that compared to the random illusion, no matter in the correctly and falsely predicted sequences, the illusion based on QA relevance causes significant changes in the prediction accuracy of ELKT models. For example, in the correctly predicted sequences, the initial accuracy is 1. And after relating 5 question answer pairs according to QA relevance, the accuracy is about 0.68, but the random illusion remains the same in the accuracy. So here we validate the QA relevance. Then we explore the hidden information among ELKT models. First, we want to explore what is the role of scale in ELKT models, because the inputs of ELKT models are question answer pairs. We use the scale index to represent the question right. We define the scale of the 15 question of each sequence as the task scale. We define question answer pairs on the task scale as task scale group TSG, and we define pairs on other scales as other scale group OSG, and we compute and compare the mean of absolute QA relevance of TSG and OSG among correctly predicted sequences. Here is the result. No matter in which ELKT model the measuring positive or negative prediction, the QA relevance in task scale group is significantly larger than that in other scale group. So we conclude ELKT models rely more on the layer's previous performance on the target scale to make decisions when they're meant as a scale effect. Then we explore whether the position in the sequence affects the ELKT model's prediction. We define the scale of the 15 question as the target scale. We define question answer pairs on the target scale in the first half as the front group, and we define the pairs on the target group in the second half as the closed group. We compute and compare the mean of absolute QA relevance between the two groups. And we can see that no matter in what ELKT models, no matter in positive or negative prediction, the QA relevance in closed group is significantly larger than that in front group. So we conclude that ELKT models tend to rely on learners' recent performance to make decisions when they're met as recency effect. And here we come to the conclusion part. To address the interpretability issue, we have introduced a generic interpreting method and proposed a 4-step procedure to interpret ELKT models. The experimental results on all the 3 ELKT models validate the interpreting method. With the interpreting results, we discover the scale effect and the recency effect from the ELKT models. All about is my presentation. Thank you.